Aloha. Once again, coming from the haven of peace, love, and physics here at the Venditto household. Look at it out there, huh? There ain't no cure for the summertime physics. Gosh, it's a beautiful day. Beautiful day. All right. Going to do two homework questions here. 55, which is the one that deals with water flowing through a pipe. And it tells you the diameter of the larger section of pipe, and the pressure in that larger section is able to support a column of water that's 10 centimeters high. When the pipe narrows, it can only support a column of water 5 centimeters high, and that hopefully makes sense, because what Bernoulli likes to say is the faster a fluid moves, the less pressure it exerts. And you know that if the area gets smaller, the velocity gets bigger. All right, so then it's going to ask you what is the diameter of that narrower part of the pipe. So that's going to be what we do for 55. 57 is the other one we do that deals with a geyser, which is pictured there, that's clearly not named after my ex-wife. Hey-oh! All right, but anyway, 55 is what we will start with. All right. I went ahead and made a larger diagram of the picture in the book so we could see it a little better. All right, so water is flowing this way, and it gives you the flow rate of the water inside that pipe, 1.8 times 10 to the negative fourth cubic meters per second. Remember, that number never, ever changes throughout this particular question, because that flow rate stays constant. Okay? And it gave you the diameter of the larger section of the pipe, 2.5 centimeters. The goal of the question is the diameter of the middle section, where it constricts itself. How wide, what is that diameter? Okay, and then remember, it supports a column 10 centimeters there, 5 centimeters there. So this particular problem is one that I refer to as a Skinnerd song, because it takes 1, 2, 3 steps. So that's what you will give me. 3 steps. The first one is to get the velocity on the left side of that drawing. So what I did with that drawing is, again, just divvy it into 3 parts. The left part, which is prior to the constriction, the middle part, which is the constriction, and the right part, which is after the constriction. All right, so there's left, middle, right. And in this particular problem, we don't even need to use the information about the right side. We're going to deal with just left and middle. So the velocity on the left is our first goal, or our first step. Remember, area times velocity is the flow rate. That flow rate was given in this particular question as 1.8 times 10 to the negative fourth cubic meters per second. That number, again, doesn't change. So if I want the velocity, all I have to do is divide by the area, which is pi r squared. Now remember, the radius is half the diameter, and I know you know that, but it's easy to get or to just forget to cut it in half. So since the diameter was given as 2.5 centimeters, the radius is 1.25 centimeters. Please don't use centimeters. We'll put it in meters for this particular question, because that's in meters. So throw it into meters. Don't forget to square it. That's the speed of the water in the left side of that pipe. All right, so it's going that many meters per second, 0.367 meters per second. Okay, so there's the first step. Now that we have the velocity in one section of the pipe, we can use Bernoulli to get the velocity in any other part of the pipe. And this particular question, we're going to end up getting the velocity of the pipe in the middle section, where it is in fact constricted. So what Bernoulli tells us is, hey, the pressure in any one location plus the fluid version of kinetic energy in any one location, which is 1/2 rho v squared, plus the potential energy Bernoulli fluid version, which is rho gh instead of mgh on the left there, is going to be the same as those same three terms everywhere else, or anywhere else, sorry. Okay? Now, the interesting thing to note is the pressures. Okay? The pressure on the left and the pressure in the middle. This diagram here has the left side of the pipe holding up a 10 centimeter column of water, and above it is the atmosphere, which I jokingly call the bank machine, the ATM, the atmospheric pressure. Same thing for the middle section. It's subject to atmospheric pressure. So the pressure that we're feeling inside that pipe is atmosphere in both locations. So the pressures are the same on the left and in the middle. So we can cancel those out because it's the same term on both sides. All right. And then what you row is, gosh, this row is the same as that row, and what you also row is it's the same as that row and that row. What do you row? So what we can do is cancel out the density of the fluid, which in this case is just water anyway, but since the same term appears everywhere in this equation, we can cancel it out. Then the last thing to do is say, all right, our goal is the velocity in the middle, which means the term that's left over here, which is just the GH in the middle, I'm going to subtract over to the other side, or just move it to the other side by pushing the minus button. And once that's there, I have to kill the 1/2 next to the V in the middle, so I will do that by doubling everything, all right? And then square root of 5, because I have to get rid of the square in the term. So isolating that, I'm going to minus the GH in the middle over to the other side. This 1/2 turns into that 2 there, and I then just carry this stuff down. The 1/2 V on the left squared, GH on the left just comes down to there, and this is GH in the middle, which was subtracted over from the other side. I did, again, double it. I went ahead and square rooted everything. That's the velocity in the middle. Okay? Now, when you do these, I always recommend pushing the square root button first before you do the math rather than after, because it's very easy for students to forget to push the square root button when you're done. So when you push the square root button, the calculator will give you a parenthesis. Go ahead and use it. Okay, so the calculator gives you that parenthesis there, then just type everything you see. 2 times 1/2 times the velocity on the left, which is 0.367. We got that in part A, or the first step. Don't forget to square it, plus 9.8 times 0.1 meter. Again, it was 10 centimeter column of water. Don't use 10 centimeters, use 0.1 meter. And we're going to subtract the GH in the middle, which is 5 centimeters, but we're going to use 0.05 meters. That quantity is what you're done doubling, and you then need to tell the calculator that you are done square rooting. So close another parenthesis right there, and there's your whole entire thing. So if you type it just like that, push the square root button first, then it gives you a parenthesis, then 2 times everything there, and then close both parentheses, enter. You will get all of that down to just, well, it's 1. So it's kind of funny, you do all that math and you end up with an answer of 1-ish, about 1.06 meters per second. So it makes sense, it goes a little faster, again, because the pipe got narrower. So it's 1.06 meters per second in the middle, compared to what you remember, it was 0.367 on the left side prior to the constriction. All right, and now once we know the velocity in the middle, then we can use the same flow rate equation to get the area, and then once you have area, just diameter. That's just an easy geometry thing. But all right, to get the area, we're going to use the same AV, area times velocity. That formula, that number given again is 1.8 times 10 to the negative 4th. That quantity doesn't change. Anywhere in the pipe, that flow rate is constant. So we're going to use the same flow rate we used in the first step, but now we're going to divide by the velocity. We just got 1.06 meters per second. Okay, that will give us 1.7 times 10 to the negative fourth square meters. Okay, those S's die, that M kills one of those cubic M's. So we're in square meters now, 1.7 times 10 to the negative fourth. It's a small number, but hey, we're talking about the area of a pipe there. Now, area for any given circle, you guys all know, is simply pi r squared. So if I are going to solve for whatever that r is, then what I are going to do is simply divide by pi and square root it. So it's that surface area divided by pi, square rooted is the radius. Now this will give you a pretty small number, 0.00736 in meters. You probably won't write it that way. I would go, 7.36 millimeters probably is what I would end up writing it as, but it's a very small number, 7.36 millimeters, or 0.007. Anyway, all right, now that's, remember, radius. This particular question didn't ask you what the radius of the pipe is. It wanted the diameter. So just double the r and you can have the diameter, which is, 0.0147 meters, which again, I probably wouldn't call it that. You might call it 1.47 centimeters. But when you all get to engineering school and start doing these types of problems more frequently, you'll never really use centimeters. Everything will be in millimeters. So I would call it 14.7 millimeters. Yay! Physics. So there's number 55. Again, a Skinner song because it takes 3 steps. Get the velocity on the left as the first step, 0.367. You use the flow rate equation. All right, once you have the flow rate equation giving you the velocity on the left, throw it into your Bernoulli equation, get the velocity in the middle, and then once you have the velocity in the middle, go back to your flow rate equation, and that's how you do number 55, a question that would certainly make the Mario Brothers proud. All right, 57 is a question that deals with the geyser Old Faithful. All right, and I went ahead and made an enlarged drawing of what they're referencing in that particular question. All right, so there's the water that gets shot upwards out of Old Faithful. I wrote the height at the S, which in this case I wrote it to stand for surface. The height of the surface, 0 meters. That makes sense. That's ground level. In the question it said, boy, water shoots all the way up to a height at the top of 40 meters. So that's how high the water shoots out of Old Faithful, 40 meters. That's like 125-ish feet. That's pretty high. It's not bad, okay? Then it said, hey, the chamber way down below is 175 meters below the surface, so I called it HC, the height of the chamber. It did say the height, the width or size of the chamber is very, very large compared to the size of the opening. That statement will become significant, and then it says, hey, the pressure then that causes all of that water to rush up is due to heating, which is caused by the liquid hot magma. So it's going to say, all right, hey, first part of this question is, what is the speed at which the water molecules leave the surface of Old Faithful? Okay? What is the speed at which it leaves? So in this, we're going to have to go back to Physics 1, where you learned the 5 kinematic formulas, where you have an initial height of 0, a final height of 40. An initial velocity is your goal. You don't know it. Your final velocity, though the velocity way up at the top, the highest anything goes, its velocity drops to 0. So you know a VF. During its ascent, gravity is slowing it down, so you know its acceleration is due to gravity, or deceleration, I should say. It's slowing down, so it's negative 9.8. You have no idea how much time it takes that water to flow upwards, do you? You have no idea, and that's the key to remembering which formula to use. It's the one I jokingly refer to as phi-vula. It's the fifth one that you learned, and so that's why I call it phi-vula, but it's the one that does not have the letter T in it. It's the VF squared. It's the same thing as the VI squared plus 2A, and in this case it's Y's instead of X's, YF minus YI, the change in Y. All right, now what I'm going to do is call the things 0 that are 0, all right? The VF, the final velocity, the speed of those water droplets at the tippity top of its trajectory is what war is good for? Absolutely nothing. And the initial height of those water droplets, the YI, is even more nothing. So those two things go away. If I want to isolate the initial velocity of the water droplets on their ascent upwards, what I will do is subtract this quantity over to the other side so I can keep that number positive, not a big deal, but that means negative 2 times the acceleration times the final height that it reaches is the square of the velocity. So if I square root that, I will have the speed at which it leaves. Okay, now remember, that negative sign isn't going to harm us under the square root, because when you put the number 9.8 in place for A, it is a negative 9.8, because gravity only works in my favorite band, one direction, which means negative Y. All right, so it's a negative 2 times a negative 9.8. The two negatives go away. They go bye-byes times 40. Square root that, you'll get 28 meters per second. Is the upwards velocity of the water droplets as it gets shot out of the old faithful geyser. Okay? All right, now, that's one option. It says, hey, figure out the speed of the water droplets. Another option to figure out the speed of the water droplets is to use conservation of energy. So if you add up all of the energies, the sum of the energy at the surface, it's going to be the same as the sum of the energy of those water molecules at the top of its trajectory. So there's two kinds of energy we play with in this particular example. mgh, which is potential, 1/2 mv squared, which is kinetic, and the S stands for the surface, and the mgh at the T at the top, and 1/2 mv T at the top squared is the kinetic. Now, you know, again, the velocity at the top is 0 because those water molecules come to rest before they come back down. You know, the height at the surface is 0 also because ground level we called nothing. All right, and then what you'll also see is then what we're left with is simply the kinetic energy at the top, or at the surface, I'm sorry, is the same as the potential energy at the top. So kinetic becomes potential. Kinetic is potential. What you'll also know is the mass of those water droplets doesn't matter, because it's like history class, we can kill the masses. So I have 1/2 velocity at the surface squared is the same thing as GH at the top. So if I do normal rearranging, I want the velocity at the surface, right? So the velocity at the surface is GH, but then to isolate this V of the S, I have to kill that 1/2, which means I'm going to multiply everything by 2 GH, and again, to get the VS by itself, I need to square root it. So 2 GHT. That should look strikingly identical to what we ended up using the kinematic equation with. It was the square root of 2G H at the top. So this was negative 2 times negative 9.8. All right, negative 2 times negative 9.8 times 40. This would end up being positive 2 times positive 9.8, because when you put the number 9.8 in place for the letter G, it's positive. Okay, that's the difference. G is positive 9.8. The acceleration, A, is negative 9.8 times the height at the top. This formula gives you the exact same answer as that one. It simplifies down to that. So that was your two options to answer part A. Part B said, well, what if we use Bernoulli in order to get the velocity of those water molecules as they leave the surface as it's getting shot out of Old Faithful. All right, so the Bernoulli equation, the pressure at the surface plus the fluid equivalent of potential energy, rho GH at the surface, plus 1/2 rho V squared at the surface is equal to the P pressure at the top of its trajectory plus the rho GH at the top plus the 1/2 rho V at the top squared. Again, that velocity at the top, 0, so I will cross it out and call it nothing. The height at the surface is also nothing. And I indicated, or I underlined the pressures. And what I'd like you to realize is that pressure at the surface is not the pressure that is pushing the water out of the geyser. The pressure at the surface is the pressure that those water molecules feel after they are shot out of the geyser. At the instant it is now exposed to the atmosphere, to the bank machine. All right, so this pressure at the surface is atmosphere. And as those water molecules get shot up and they're at the tippity top of its trajectory, the pressure they're feeling is also atmosphere. Even though it's 40 meters high, atmospheric pressure doesn't really change over 40 meters. So the pressure at the surface is the exact same as the pressure at the top, and since they're both the same, you can cancel them out, and that will reduce the pressures, or reduce the number of terms there. So now again I'm left with 1/2 rho V at the surface squared. It equals rho GH at the top. And again, in the same manner up here, we could eliminate or kill the masses. We can kill the densities in here because it's a rho and a rho. And what you rho is it's the same stuff. So those fluids die. And what you'll notice is it's a 1/2 V at the surface squared is the same as a GHT, which is exactly the same thing we were left with up here. 1/2 V at the surface squared is equal to a GHT. So again, Bernoulli would absolutely agree with the energy. See, it's the exact same formula. So what I'm left with for the velocity at the surface is that GH. And again, to get rid of the half, I got to double it. And to kill the square, I got to square root it. So the velocity is 2 GHT. It's the same as that. 2 GHT, it's the same as that. It's going to be 28 meters per second. Okay? So there's part A and B for 57. Part C for 57 now is the one where it wants to know what is the pressure down in that chamber due to the heating from the liquid hot magma. Okay? Remember, that chamber is 175 meters below the surface. That's deep. Huh? The water is pushed up to the surface, and it did again say that the area or the size of the chamber is very, very large compared to the size of the opening. So what that means is the velocity is something that can go away. I will show you that. So again, Bernoulli, pressure at the surface plus rho GH at the surface is the same as 1/2 rho V squared at the surface. Then we set that equal to the pressure, the rho GH and the 1/2 V squared somewhere else, and it's the CH is what I used to abbreviate down in the chamber. So the same terms down in the chamber. First of all, it wanted to know the pressure in the chamber that is over and above what the atmosphere already feels. So if it's above what the atmosphere already feels, then what I'm going to do is take atmospheric pressure, which is again what it feels at the surface. The instant it's exposed to the atmosphere, that's what it feels as atmospheric pressure. Since we want to know what it is above that, then I'm going to take that pressure at the surface and call it the number of miles I jogged last week, 0. Okay? So that is going to be set to 0. That means this will be whatever it is after we've removed atmospheric pressure to call it above it. Now the height in the chamber. This is something else that I can eliminate because it told you it's 175 meters below the surface. But if I just change it and call it 0, then that height of the chamber becomes 0, and the height at ground level at the surface becomes 175. So I'm going to call that nothing. And the velocity inside the chamber is the speed at which the water rises inside the chamber before it gets shot out is also going to be 0. That's why they used the phrase the size of the chamber is very, very large compared to the diameter of the opening. All right, that means it's a very large opening or a very large chamber. So the speed of the water as it elevates inside the chamber is essentially 0. Once it gets constricted and shot out is when it goes much, much faster. So since these two terms already died, I'm looking for pressure in the chamber. There's really nothing left to rearrange. All right? Pressure in the chamber is already isolated. It's rho GH at the surface, 1/2 rho V at the surface squared. And the density of water, you guys all know, is 1,000 kilograms per cubic meter. You all know the planet we're on, 9.8, that's meters per second squared. And the height at the surface now is 175 meters above the chamber. All right, so again, since I called the chamber 0, that becomes positive 175. To that I'm going to add 1/2 times the same density, 1,000, that's kilograms per cubic meter. And the velocity at the surface is what we got in part A. It's 28, and that's meters per second. And we square that in this particular formula. All of that is what the pressure in the chamber is equal to. And so you do all that math, and you will get 2.1 times 10 to the 6th pascals. That's a lot of pressure. Someone should write a song. Huh? Now, an interesting thing to note is the units, all the letters. It's there's a lot going on with the letters in this particular one. So what I'm going to do is rewrite the units and just show you what happens because it's interesting. This is just the letters now. Kilograms per cubic meter. I'm going to multiply that by a meter per second squared, and then I'm going to multiply that by another meter. Okay? Those are just the units now. And it's interesting, again, to note what happens to those units. The first thing I'm going to do is combine them in a somewhat strange manner. I'm going to take this kilogram and combine it with that meter per second squared. So there's kilogram meter per second squared. KGM/S2. That's how you spell the letter N. That's a Newton, the metric system unit for force. Newtons, I forget who they're named after, but that's the metric system unit for force, Newton. Okay? Now, what I will also do is take that meter and kill it with one of the cubes of that meter. And that will give me a Newton per square meter. That's a Pascal. All right? So it's interesting to note that this Newton times a meter is in fact a joule. If you remember that from physics 1, there's a Newton meter. That's a joule. A joule per cubic meter. Or you could say, hey, a joule or a Newton per meter, a Newton per square meter. A Pascal exerted over a distance. Pressure exerted over a distance, if you then multiply it by another m, is the ability to do work, right? A Newton meter, pressure times a distance, can do work due to the heating of a chamber. And so this interesting combination of letters to give you energy, joules, work, pressure is neat to say. It is the basis of thermodynamics. That will be our next topic in physics 2. All right, and the interesting thing to note is over here. we're going to add, we push the plus button, so these units have to be the same as the ones over there, and so I will rewrite them. They are a kilogram per cubic meter. To that, I'm going to multiply it by a meter per second. But remember, that's squared now. We don't discriminate in physics. If you square the number, you also have to square the letters. So it's a meter squared per second squared, okay? And you see how this meter squared per second squared is the exact same thing as this, which is a meter times a meter per second squared. So this m times m is the same thing as the m squared right there. This second squared is the same as that second squared, and this kilogram per cubic meter is the same as that. So these units end up simplifying down to the same thing those units do, a Pascal, which is why we're able to push the plus button. But again, when you have a density times a velocity squared, you get, again, the unit that is pressure. And it's just an interesting unit. Follow the letters. I use that phrase a lot. All right, so summertime physics, gotta love it. Beautiful day here in Cincinnati, and yay, physics. Aloha.